All right, hello KansasFest. Sorry I wasn't able to make it in person for my session on Saturday, but I wanted to record some content and put it up there. So, one to be available for everyone who's at Rockhurst right now, and then there would be something for the virtual conference and the Q&A session that's scheduled then. So my session is porting a classic game to a classic computer. This is kind of a continuation of the work I presented at KansasFest last year on the generic tile engine uh, library. I was kind of playing around with it. We made a lot of improvements over the last year and looking for kind of an opportunity to test it out on. And I thought, well, it's designed to be similar to the hardware for a Nintendo. So let's see what we can do in terms of porting an existing game to the tile engine. And things actually ended up going really well. Started this project I think back in just April, and really within 4 to 6 weeks, a lot of it came together. So I'd like to go through and kind of show you what we've done and how it kind of maybe opens up a possibility of bringing some new ports to the 2GS. All right, so first things first, kind of a comparison of what we're working with. So we have the Nintendo on the left, our 2GS on the right, and kind of their respective capabilities. The 2GS has a better CPU, but that's really pretty much it. We can display more colors, slightly higher resolution, but the lack of any hardware support really kind of kills graphics performance, as everyone knows. The good thing is audio-wise, we're above the Nintendo, but the lack of hardware sprites, hardware scrolling really makes it challenging if we're porting something that has scrolling backgrounds or is kind of a platformer style game. And then before I dive into it, just a quick reference of kind of the things I've kind of leveraged when I was going through this project. The biggest one is there's a very good disassembly of the Super Mario Bros ROM available out on GitHub. I think it's been out for over a decade at this point. And then the fact that there are lots and lots of really good resources out there on how the Nintendo hardware works, and all the details of how to get it to perform correctly, given how the games drive the hardware. That saved probably months of work, just that being able to reference both the documentation as well as other emulator implementations to see how they simulated various functions in their software implementations. So I'm going to cover kind of three major areas on how this port happened. First, how the code got ported over, kind of the different things that had to be done in order to get the native 6502 code running on the 2GS and running within the 2GS environment. I guess just a heads up, the end result of this is a standard GSOS 16-bit program. You can run it from the Finder. It's not a like a prot.sh just loads into memory and does whatever it wants. We try to be well behaved. After we look at the code, kind of talk about both the video and audio portions of the NES, the PPU and the APU, and how we hook into those and try to simulate those capabilities on the 2GS. And for the PPU in particular, leveraging some of the capabilities of the GTE library to make it much easier to map the functionality between the two systems. All right, so porting the code. The gist that is available can almost be used as is. There's going to be some minor syntax changes that had to be made, but the biggest work is these items 2, 3, and 4, which is what do we have to do to set up a proper execution environment so that the NES code can run the way it expects? How do we drive it from our controlling application? Because NES games are primarily interrupt driven. They have a interrupt subroutine that gets triggered every VBL. They run their code, they set up the hardware, and then they effectively busy wait until the next interrupt comes in. Obviously, we can't do that. We have to do other work while the Nintendo code is waiting, so we have to sort of simulate that interrupt-driven environment. And then kind of going the other way, instead of driving the code in the ROM, how do we have the ROM hook into our application code in order to know what's going on in terms of hardware rights, how it wants to control the hardware, graphics, things like that. All right, first things first, the syntax. Like I said, it was pretty minor changes to get the code up and running. The gist, I'm not sure exactly what assembler they're targeting, but other than putting like colons after the labels and using .dw and .db instead of dw and db, I guess just for reference, I'm use the Merlin 32 assembler for all of my cross-platform coding, so that's the syntax we're targeting. All of this was really just search and replace to get them syntactically working, and really the code kind of just compiled at that point, which was really nice. Now the execution environment was a little more of a challenge. So we're not running the ROM code in bank 0. We want to relocate it to a higher bank because obviously GSOS needs to use bank 0 for its own purposes, and we don't want to be restricted in that way. So obviously we're running on the 65816. We have a separate direct page register. We have a separate stack pointer. We want to use those to simulate or to give the NES code its own isolated execution environment. But of course the challenge is that 6502 code is going to assume that the 0 page is at 0, the stack is at address 100 and up, and so we're just going to have to see if that causes us any problems, and spoiler alert, it did, but we have to deal with that. Then I'll show how I'm driving that ROM code, and then also how I've implemented the hooks to come back into the application. All right, so first step, giving the NES code its own 0 page and stack. This is actually pretty simple. So GSOS applications, when they start up, they are by default given 4 kilobytes of shared direct page and stack space. The direct page is pointing to the bottom address of that 4K range, and the stack pointer is at the top of that range. So what we do is really just take some of that and allocate it for the Nintendo. So in this particular example, I'm adding 300 hex to the base address because I need a few direct pages myself. That is what we set for the ROM 0 page. Then we add on 1FF to set the stack to the top of the next page. So that's our 512 bytes of Nintendo RAM that we allocate there. Now there's a few problems that come up when we do this. And 3 problems in the sense of there's 3 specific pieces of code in the ROM that breaks when we don't have 0 page at 0 or the stack at 100. The first one is there's a core subroutine in the ROM called the jump engine, and this is pretty much responsible for driving all of the event processing in the ROM, and it relies on indirect absolute jumps. So the jump indirect 6 instruction is going to jump from ROM address 6 down in 0 page, and then it's going to go to the address that's found at that memory location. So obviously that's not going to work because our 0 page is not in bank 0. But fortunately, we can get around that because we're in RAM instead of ROM. The other thing we have to deal with is an initialized memory routine. It was pretty simple. It just goes right through all the pages from page 7 down to 0, sets it to 0, and then it's done. So we're going to have to intercept that to clear stack and 0 page in their actual memory locations, not in the same bank that the NES code is. And then finally, and this is the most complicated thing to fix, they used a lot of absolute Y index code to reference 0 page variables. So there is no 0 page indexed Y instruction, not even on the 65816, which would have been really nice. It would have saved a lot of problems. So that always gets assembled to a 16-bit address indexed by Y. And basically we have to go in and rewrite all of that code to be equivalent but not use that addressing mode. So how do we deal with that? So one by one. So dealing with the indirect jumps, in this case, because I said we're in RAM, we just do some self-modifying code. So instead of jumping to address 6 here, we take those bytes that would have been stored at those locations and instead store them into the address of this jump target and then jump to that. So that was actually a pretty easy workaround. Kind of once you realize that you don't actually have to use the same instruction, we can modify that in a different way. Similar, the memory initialization was pretty straightforward too. The fix here was to simply terminate the loop early. So we stopped clearing data after we finished page 2, and then just jump to a separate subroutine that initialized the proper RAM using 65816 instructions to get to the memory of our direct page and stack. And then finally, how do we deal with the direct page Y index? Pretty much it was a replace of every time there was a load or a store, we would preserve the Y register. We would put the Y register into X, use the existing direct page X instructions, and then restore the X register here. And I think there was about 150 locations that had to be patched in like this to make it work. And fortunately, and this was fairly lucky, the disassembly for this ROM was good enough that we didn't have to keep everything in the same memory location. So the NES ROM is 32K total. The code starts at 8,000, and then it goes up to the interrupt handlers up in FEFF. And it turned out that we can add extra code and then just move the origin further down into memory into the 7,000 range, and everything works. There's nothing that is hard coded to any addresses in ROM. So that was quite a relief and gave a lot of flexibility in how to rearrange and modify the code. All right, so then the next step, like I said, once we have the kind of the ROM code itself working the way we want to, now the question is how do we drive it like the NES hardware? So the main thing is we need to come in and every VBL interrupt execute the game logic. And to do that was really kind of just a little bit of a dispatch code where we do kind of the usual thing you would expect of saving the current registers of the execution environment and then resetting the stack, setting the bank to the NES ROM bank, setting up our 0 page and stack pointers, and then there's a little hook in the ROM code itself that we do a long jump into in 16-bit mode, and it's responsible for then switching back into 8-bit mode and dispatching to the appropriate bit of ROM code, as well as doing a long return back. So devil in the details, but it's a kind of straightforward conceptually. And then here's that little bit of code that's in the ROM that takes care of coming in. We have a entry point, again, do a bit of self-modifying code, 16-bit store, switch to 8-bit mode, jump to the ROM code, and then come back. And this is useful too because there's actually there's 2 entry points we need to get to in the ROM, the reset entry point and then the non-maskable interrupt entry point, and those get driven at 2 different points. All right, now we kind of get into the interesting part, which is how do we hook the hardware code into our application. So what is nice is that everything in the NES is a memory mapped IO. So there's just memory locations that get written to, and those command the hardware. And when I was first looking at this, the initial idea I had was, well, all of these stores and a few loads, they are all absolute address loads and stores, so they take up 3 bytes. So, well, wouldn't it be straightforward? We'll swap out those 3 bytes with a jump and jump to some bit of memory that's outside of the ROM space, and from there we can do whatever we need to hook into our application and code. And in fact, that is exactly how we ended up doing it. And it pretty much worked the first time. There weren't any problems in the ROM that the ROM was doing anything tricky, or where doing a subroutine call would somehow trigger bugs in the ROM. The hardest part of doing the hooks was actually simulating a load or a store. And the reason why I say that is because we needed to do extra work. So here's an example of where we're triggering the PPU status register. We jump along to our subroutine that is in our application bank, and we're just trying to simulate a read, just a load from an address. But the problem is that we need to do a bunch of checks on this to make sure that we don't actually disturb the state of the CPU. So we don't want to accidentally change the carry flag. We don't want to actually change the zero flag and things like that. So pretty much everything gets wrapped up in PHP and PLP instructions. And then we also have to be careful that the very last thing we do for a read simulation is whatever data we've read, we want to store it and then pop it at the very, very end, so that the processor status flags do reflect that this value was read, and then we return, and then flags are set appropriately. There were a few really tricky bugs to track down that were the cause of that, where the zero flag was getting changed by my hook code, and that caused changes in behavior in the ROM code. But usually it wasn't localized. It was some distance down where they were actually testing those flags. All right, so now that we kind of know how we're hooking into the PPU, what actually do we need to simulate? So there's really two big chunks of the PPU. One is how it accesses object attribute memory, which is all the sprite information. And then there's the general data and address registers, which allow the ROM to write tile data into the PPU RAM, as well as read data if that's desirable. For us, that's really what we need to take care of in terms of implementation, controller logic, and then those data latches back and forth. Now, one thing that we can't do is sort of a naive implementation. The 2GS is just too slow to try to refresh from the PPU back to RAM every single frame. So we need to be smarter about what's going on. So in order to try to reduce the amount of work, there are three main things that we're trying to do. We're going to reduce the number of tiles that we write, since we know that the 2GS screen is smaller than the NES VRAM space. We can cull some writes to that. We can also be careful to not redraw tiles that don't change the current backing store, so kind of a dirty tile update. On the sprite side, same thing. When sprites are off screen, we don't have to draw them, and we can ignore certain sprites as well. As you'll see, there's actually sprites that are transparent that really don't contribute anything to the on-screen display. And then finally, and this is where using GTE kind of comes in, we can track scrolling in the game, and that really minimizes the amount of memory we need. We can hook in and make sure that we're only drawing tiles that are coming into the current visible view of the engine, rather than every single tile that the game code has changed in the previous frame. So here's an example of those optimizations, using the Messen emulator here to kind of show the differences here. So here's a scene, and you can see visually it looks like the player should be 4x4 sprites, 16 by 16 total. The coop over here is a slightly different size, but if you look in the emulator itself, this is how many sprites are actually used. So they actually use 8 sprites for the player, and 6 sprites for the enemy sprite, and there's 5 of these sprites that are fully transparent and simply don't contribute to the screen. So we take note of those IDs and then skip them. And this is kind of an important point too, which is, what we're doing here in this port, it's not generic. There's a lot of logic on the application side that is using knowledge of the game itself in order to perform a good mapping between what the code does on the 2GS side and compare it to what's going on in the game code itself. The other one we can get rid of is Sprite 0. This is used for the split screen effect in Super Mario Bros. To keep the top scroll from moving, but we can just configure the screen to do that ourselves. We don't need to simulate the Sprite 0 collision logic. So since we don't have to simulate that, we don't have to draw that. All right, the other thing we can look at is here the X and Y positions. So anytime there's a sprite that is off screen, the Y is set to a large value. In this case, I think it's set to 248, so it's down off the bottom of the screen. We filter on that and don't draw anything that is off both the NES visible area as well as the 2GS visible area. Okay, so that kind of covers how we deal with the sprites and tiles, kind of the core graphics data side of things, of hooking the PPU into the 2GS side. But now let's talk about colors. So the Nintendo has a pretty small color palette. I think only 52 or 53 colors, but it can display up to 25 colors on screen. It has 8 palettes of 4 colors each. The first color is reserved as a transparent color. So you end up with a total of 13 colors for the background tiles, and then another 12 colors that the sprites can be. So you get a total of 25 colors. But on the 2GS, we can only display 16. So what are we going to do? And we're not going to do multi-palette cleverness there. That would pretty much be impossible, because it doesn't really solve the problem, because you could still have multiple sprites and tiles on the same scan line, and so you still have the same problem to deal with. There's kind of a couple of ways that we could approach it. So one would be to reserve 12 colors for sprites, since they're the most active part of the screen, and then use a single palette for all the background palettes. Just use like a shared grayscale or something like that. That is okay, but it doesn't look great. Some of the levels look okay. You can see here on the Bowser Castle, like, it doesn't look terrible, but if you compare it to what it should look like, we're missing the lava, the bridge color, and a few other things. And then other levels kind of look worse. So colors are off. It just is not the greatest view. So what can we do about this? Well, if we look at the palette for a particular level, this is what it is on the right hand side. You see the top 4 rows are the background, the bottom 4 are the sprites. And there are a few special colors in here. So there's the background color, which is kind of the default, up kind of in position 0. In terms of the gameplay, this second color of the 4th background palette is the one that is doing the color cycling. So all the coin blocks and the coins, when they're pulsing their yellow color, it's this palette index that's changing. And then there's the 2 colors on the player palette. The player uses the first sprite palette. These colors change based on your power-up status, so they need to be handled separately as well. So we start off with kind of 4 reserved colors. So we're left with 12 colors in the 2GS palette, and figuring out how we can map those. Now what's nice is if we look through here, even counting these colors, we only have 13 unique colors in the palette. There's quite a few colors that are shared both between the sprite palettes as well as the tile palettes. So based on that, came up with this idea. So we have to talk about kind of how sprites are stored in NES ROMs to start with. First of all, they're not stored in linear order. They're stored in an interleaved format. So if you're looking at the sprite data, there's 1 byte here that encodes the low bits of a pixel, and then 8 bytes beyond that is the byte that holds the high bits of the pixel. Pixels are all 2 bits because pick one of the 4 colors in a given palette, and then they're interleaved. So the character ROM data, the raw sprite data, there's the 2 bits that pick the color index, but then you have to pick which palette you're picking, and that's in the PPU attribute table. So there's 2 bits there as well that get mixed in to give you the final on-screen color. Now, what's interesting about this is the most efficient way to get data onto the 2GS screen is to do things 16 bits at a time, so 4 pixels at a time. Well, 4 pixels in NES space are defined just by 10 bits, 2 bits per pixel, and because everything is arranged in tiles, the tile itself, the tile has an attribute. It's not per pixel attributes, so you end up with 4 sets of 2 bits for the pixels, and then 2 additional bits to define the attributes for those pixels to define the palette selection. So you end up with a total of 10 bits from the NES side of things that would get translated into 16 bits on the 2GS side. So 10 bits is small enough that we can just make a lookup table for everything. So there's some code that generates what is called swizzle tables inside the application, and all it is remapping tables. So for one level, we define for the 8 different palettes which Apple IIgs color index those should be mapped to. And then we define what the palette is in terms of NES colors. There's a separate lookup table that maps the NES colors to RGB. So we can initialize a palette with the NES palette or the NES colors, and then the data gets mapped through these. So you can see the table. You can see the structure here. So like, let's just look in the corner here. So color 0 goes to, or color 1 goes to 2GS index 2, 2 goes to 3, 3 goes to 4. So if we look through here, 0, 2, 3, 4, 2, 0, 2, 3, 4, 0, 2, 3, 4, and then the high nibbles are just strided versions of that, 0, 2, 3, 4, and then the same pattern goes down vertically. So what we can do then is in the blitting code, that is part of the GTE side of things, when we're actually drawing sprites or tiles, or really just drawing any tile data, we can use just a single extra load, or load or OR right here, to load the raw data into the index register. So right here, this is loading that 10-bit value in the tile data into the Y register. And then down here, when we're putting the data on the screen, we're looking up what 4 pixels that 10-bit value maps to through the lookup table. And what that lets us do is we can define an arbitrary remapping of colors, and it only costs a single extra instruction when we're drawing them to the screen. And the net result is we have a screen like this, where we have all the colors represented, tiles and sprites, and fortunately every single level in the Super Mario Bros ROM can be remapped into the 16 colors. There's no combination that I found so far that has more than 16 colors, and even if it did, then we can just make some choices to mix down and choose which colors to remove from the NES and remap into there. So it's very flexible, and it was really kind of a nice solution to the color mapping problem that didn't require too much of a hit in terms of the performance. All right, that pretty much covers the graphic side of things. So now let's take a look at our last bit, which is how to do the sound emulation. So we have 5 sound channels in the NES, but we're only going to emulate 4 of them. The Super Mario ROM doesn't use the DMC channel. There's the two square wave channels and the triangle wave, and then there's a noise channel. And pretty much the core of the APU is there are a bunch of timers inside the APU chip that are counting down, and when they count down, they change some value in the output, either frequency, volume, or something else. And those timers, their durations are set by the various control registers for the APU. And then internally, the APU is updating those timers at 240 hertz. So even though the NES is only updating the registers 60 times a second, it can then set timers, and the volume or the frequency can be updated up to 4 times between frames, if you're going for kind of full fidelity. So let's just take a look at kind of what's going on in each wave. So the pulse wave is pretty simple. It's a square wave. There's the various counters around there to control volume sweeps, and things like that. The length counter is basically a duration counter. Once it reaches 0, it cuts off the volume. So you see basically each of these gates is different conditions that causes the sound to terminate. The kind of interesting bit here in terms of how to implement this within the 2GS is the duty cycle parameter. So the square wave channel has 4 different duty cycles at 1/8, 1/4, 1/2, and then a reversed 1/4 period, and it can be selected, you know, at any point which one to use. So we need to have multiple waveforms backing each pulse wave. The triangle wave is similar, but it's actually simpler than the pulse wave. It has 2 counters that can each terminate the sound, but it doesn't have the sweep function for the volumes and things like that. And then the noise channel is simple as well. It's very similar to the triangle counter. The only difference here is there's no explicit frequency setting for that. Instead, there's this 4-bit value, this period value, that then looks up a set of fixed values to use for the actual frequency when it runs. So the implementation is slightly different in terms of interpreting the control registers, but how the hardware actually works is very, very similar. The trickiest thing to do when I was implementing the audio part was actually figuring out what the right frequency was. So on the Nintendo, the frequency is tied to the CPU rate, and then that 11-bit timer that I was talking about, and that's the timer that doesn't exist on the noise channel. It's the value that comes from that lookup table. So there's formulas online for what the frequency is given one of those timer values, and then from the 2GS hardware reference for our configuration, where we have 32 oscillators enabled, which is the standard, usually the standard config. The frequency of the 2GS output is this constant times the value that you put into the DOC frequency registers. So since we have these two frequencies together, we can then kind of rearrange things and solve for the DOC register value based on what the 11-bit APU timer value is. And it turns out to be this function, which is not terrible to implement. Anytime we have to change the frequency, we end up doing a 16-bit divide and then some shifts to do the multiply by 10. Again, this is one of those things that kind of just worked. Did the math, implemented it, and the output sound was pretty close to what you would remember coming out of a Nintendo. And I mentioned too on the duty cycle parameter for the square waves. In order to handle that, we just have a separate waveform for each of those duty cycles. When that APU register changes, then we update the DOC register value to just point to the appropriate page of DOC RAM to play that cycle. Triangle wave and noise wave, they're constant. They live in their own banks. And keeping every waveform to 256 bytes means that pretty much everything has the same fundamental frequency, so it just makes the math easier. I'm sure there's a lot of things that I'm doing wrong. This was the first time I did any sort of audio programming on the 2GS. I've kind of avoided it all these years because it seemed fairly intimidating. It wasn't too bad to get something to come out, but I'm sure there's a lot of things I could have improved in the audio part of this. And kind of to help that out, so one of the tools I created as part of this effort is something that's called APU Sim. It's patterned after this live ROM that's available. It can be downloaded to run on an emulator, and it has a pretty much this interface. I copied the interface almost exactly, and it lets you just go through and tweak different register values for the different APU registers. So I ran that ROM in a Nintendo emulator and had this tool running on my 2GS emulator and did a lot of comparing of behaviors and sounds and things like that to get them close. If you run them side by side, I'm way off, but it's surprisingly good enough for the end result. And speaking of the end result, I've just talked a lot about everything that's happening in the abstract. So let's take a look at how things turned out. So what I have here is this is running in GS port. Let me hide this. There we go. And I'm going to set the speed to something more reasonable, and we'll see how it turns out. So one thing I was trying to finish up just before KFest was this part. So obviously running full screen is not feasible, especially on real hardware. So we've got a video selection, good, better, best. Best runs a full 200 lines tall, gives you kind of the closest thing to the original gameplay as you can. Good and better shrink the playfield, but because we're tracking ROM variables, we can scroll as needed to keep everything centered in the playfield. The audio quality, the good, better, and best. Best runs the APU emulation at a full 240 hertz using the DOC interrupts. Better cuts that down to 120 hertz and just basically doubles up on the work in each interrupt. And then good turns off DOC interrupts and updates the APU during the VBL, so we get less interrupt overhead as well as less work in each interrupt. Just for now, I'll put it on best quality for both, and then I'll come in and we'll look at good quality. Tried to pick a 6 there so we can see that everything is working. Alright, now let's take a look at the good quality so you can see what's going on with the different scrolling abilities here. So video quality good, audio quality good, we'll just start with that. So as you can see, the screen is significantly shortened. Also, the status bar is no longer part of the playfield. with that, that is the work I have been doing on the last few months. So I'm happy to share it with everyone here at KFest. I will have the disk image of this in the Discord channel shortly. And thank you all very much. Sorry I couldn't be there in person this year. Hope to be there next year. Bye.